Let's move on to conjugate beam method. This method is developed based on some mathematical analogies that we identified from two sets of equations. The first set of equation is m over ei, slope and deflection. They are related through these equations. So d theta over dx equal to m over ei, dy over dx equal to theta, and here is the moment curvature equations. The second set of equations is relating to load, shear, and bending moment. They are related through dv over dx equal to w, shear force, and this is loading. And then dm over dx equal to shear force, and finally is d squared m over dx squared equal to w. So you can see that mathematically they look exactly identical. So if we can further establish mathematical equivalence like this, then basically their calculations are exactly identical. That is, if we can relate m over ei to loading, relate rotation angles to shear force, and relate displacements to bending moment, then the mathematical operations that you conduct on the left will be exactly the same as the mathematical operations that you conduct on the right. So quite often we are asked to determine displacement and rotation angles under certain loadings. So that is, we are doing calculations on the left. So now we have identified this mathematical equivalence. If we can convert all the left-hand side parameters to the right-hand side, and then perform the calculations on the right-hand side, then we can, after we obtain the results, we can convert the right-hand side results back into the left-hand side. So that's the idea for the conjugate beam method. Now the reason for doing that is we are very, very sure or very, very experienced in calculating shear force and bending moment from loading. So this is basically just equilibrium calculations. So we are far more familiar with this set of calculations than the calculations on the left. So let me use one example to illustrate this concept. So this is a cantilever beam. Clamp on the left, and there's a point load pointing upward, P. So you can do equilibrium calculations and find out bending moments and m over ei plots. So instead of moving on using direct integrations or moment area calculations, we can try this conjugate beam methods. But the idea is you need to convert from the left to the right first. So by that, I mean that you need to move m over ei and then impose on the right-hand side as a loading. And you also need to convert rotation angles to the right-hand side in terms of shear force, and displacements moving to the right-hand side in terms of bending moment. So here is the starting of the conjugate beam. So I need to do the conversions of the three parameters to the right-hand side. So noted that the claim boundary conditions tells you that rotation angle and displacement should be equal to 0. So we also need to convert rotation angle and displacement to the right-hand side, which is corresponding to shear force equal to 0 and bending moment equal to 0. At the free end, rotation angle is not equal to 0, displacement is not equal to 0. So converting to the right-hand side, shear force and bending moment, they are not equal to 0. Now, the boundary conditions that complies to shear force equal to 0, bending moment equal to 0, actually is a free end. On the other hand, the boundary conditions that complies to shear force not equal to 0 and bending moment not equal to 0 is actually a clamp end. So basically, we are converting displacement to force conditions that basically change the support conditions of the beam. That's why we have this name conjugate beams. So this conjugate beam is not a real beam. It's just a mathematical constructed beams that helps you to follow the right-hand side calculation. So after you establish this conjugate beams, then you convert M over EI to loading and impose it on this conjugate beam. So here, this is M over EI that you obtain from the real beam and then impose it on the conjugate beam. So after that, all you need to do is to do WVM calculation. Then you further calculate shear force using equilibrium and then bending moment using equilibrium. And according to the mathematical analogies that we established, the shear force you obtained on the conjugate beams is equal to the rotation angle on the actual beam. So this is the rotation angles for the actual beam. And this is the displacement for the actual beam. So I just show you a very quick illustrations how you can convert from actual beams to conjugate beams. So here are the mapping table to help you establish such a mapping very quickly. So for instance, this is the real beams conditions and this is the conjugate beams condition. If I have a hinge end, the rotation angle is not equal to 0, but displacement is equal to 0. So rotation angle corresponding to shear force, displacement corresponding to bending moment. So it tells you that at the conjugate beams, the bending moment is equal to 0. So the result is if you have a pin support on the conjugate beams, remains a pin support. If you have a roller support on a real beam, it will become a roller support, remain a roller support. If you have a clamp support, then it will be converted to a free support that we just showed in the previous example. If we have a free support, then it will be converted to a clamp support. If you have an internal pin comes with rotation angle but not displacement. So shear force is not equal to 0, bending moment equal to 0, which is corresponding to an internal hinge. So if you have an internal roller, again, it's an internal hinge. If you have an internal hinge, it's actually converting to an internal roller. And here are some examples of real beams and conjugate beams pair. Next, I'm going to use this example to illustrate how you can use the conjugate beam methods to determine rotation angle and displacement for this structure. First, you obtained bending moment diagrams. Divided this bending moment diagrams by EI. So you obtain M over EI plot, which will be used to act on the conjugate beams. Next is to convert this beam to conjugate beams. As I just showed you, that the end support or end hinge remains hinge, and internal hinge become internal roller, internal roller become internal hinge, internal roller become internal hinge, internal hinge become internal roller, and roller remain end roller. So here is the conjugate beam. Next, you just take M over EI and then assume that it's a loading acting on the conjugate beams. Then you can perform equilibrium calculating shear force and bending moments inside this conjugate beam. And the shear force inside this conjugate beams will be corresponding to the rotation angle at the same locations of the structure in the real beam. Also, the bending moment will be corresponding to the displacement of the real beam. I'd like to make comments to the three methods that we just introduced. The direct integration method. The method is conceptually straightforward, but it could be computationally complex because it involves setting up different support conditions. The second method, moment area method. There are two methods. These two methods are rather indirect because they tell you the relative rotation angles between 2 points, or they tell you the relative projected distance between the 2 points. The third method, conjugate beams method. This method is conceptually complex but computationally very robust because it relies on equilibrium calculations. Note that all these three methods, they can be applied to simple structures. But when you want to extend it to more complicated structures, these methods might be very difficult.